right, hello chemistry students. Today we're going to be talking about the kinetic molecular theory of gases, which is a way for us to describe the motion of gas particles conceptually. We're going to be learning about this mathematically in just a few days when we talk about the combined and ideal gas laws. This is just a way for us to imagine how these particles are moving in a given situation. Now, whenever we talk about the kinetic molecular theory, there's 7 variables that we want to make sure that we touch on when we're kind of thinking about each situation. The first one is the container type. Is it open or closed? Is gas able to enter and leave freely, or is it sealed off? Is it trapped inside? Is it flexible or inflexible? Can the volume change like a balloon, or is it constant? Is it a rigid container? The second variable we want to consider is the moles. How many gas particles are trapped inside? It's just literally, what's the number? The third variable we've talked about before, temperature. Remember, this is a measure of the average kinetic energy. So this is talking about the motion of those gas particles. Now that's related with number 4. So 3 and 4, the kinetic energy, these are always going to be directly related. Whatever the temperature does, the kinetic energy is going to do. And specifically, when we look at kinetic energy, remember from physics, it's the equation 1/2 mv squared. So there's a relationship between the mass and the velocity of those particles. Larger particles are going to travel at a slower speed at a given temperature. So there's this relationship. The lighter the particle, the faster it's going to be moving. This will come back into play a little bit later on, but it's something just to take note of now. The last 3, collisions, pressure, and volume. Collisions and pressure are also going to be directly related to each other. Collisions are just literally the gas particles bouncing into the walls of their container. Now, if we measure those collisions, that's pressure. Now, typically, we're going to use the unit of atmospheres when we talk about pressure, but again, that's going to be something that we get to when we get to the math a little bit later on. Volume, the measure of how much space that gas takes up. We've talked about volume all year. That one's going to be consistent. Now, 4 of these variables are going to come back when we get to the combined and ideal gas law. So we're going to be using moles, temperature, pressure, and volume. So we'll come back to these mathematically. This is just the conceptual explanations first. Now, one of the tricky things is determining the type of container when you look at a problem. And oftentimes it depends on the specific situation. A balloon, for example, it's flexible, but whether it's open or closed depends on whether you have a knot tied in that balloon or not. If it's open, gas can freely enter and escape, whereas the knot seals it off. An aerosol can generally is inflexible. Its volume does not want to change. However, it's got the button on top. If you depress the button, you are opening that container. The gas particles inside can now escape. Whereas if you don't press the button, it's considered to be sealed off. A syringe depends on both fronts. The volume of a syringe can change depending on the plunger. We looked at that yesterday. You can depress the plunger and decrease the volume, or pull the plunger out and increase the volume. You could put your finger over the end and seal it off, or you could leave your finger off and have it an open container. So you really have to pay attention when you're looking at a particular situation as to what type of container that situation is describing. So let's just do a bunch of these together. Let's go through and practice this idea. The first one we want to look at is, imagine you have an aerosol can and you're adding more particles to it. Now, when we fill the particles into the can, we want to first identify what the change is and then go through all 7 variables. So before I get to the actual change, I want to think about what type of container an aerosol can is. Now, this container is closed. Nobody is depressing the trigger, so it's sealed off. No gas can get in or out other than we are manually or forcefully adding particles to it. And it's also going to be inflexible. Now let's think about what we're doing. If I literally look at the before and after picture and count the number of dots, I see that there's an increase in the moles of gas inside that container. So there's more particles in the second container. And if I think about the motion of those particles, I know that those particles are flying around that container, and I can draw some arrows to show the motion of those particles. Now, the size of these arrows is determined by their temperature, how fast those particles are moving. Now, we're not changing the temperature of this can. So we can think about the sizes of the arrows as more or less the same. So if I have more particles, but they're moving at about the same speed, as those particles are moving around, more of them are just naturally going to lead to more collisions with the walls of the container. There's just more of them to bounce off the walls. And if I think about my variables up at the top, I know that collisions and pressure are always directly related. So more collisions will lead to more pressure. Now, I always want to ask myself, how does the pressure inside the container compare to the pressure outside of the container? And typically when you start with a container, the pressures start equal. If we're raising the pressure inside of the can, outside pressure doesn't change. I know that the inside pressure is going to be greater than the outside. An aerosol can is pressurized. It's got a lot of pressure inside. Now, oftentimes in these situations, there are variables that don't change, some constants. Well, the volume of the container didn't change, right? We left the volume of the thing the same. Temperature and kinetic energy stayed the same. Now, you can make small arguments of, well, you added more particles, so the mass went up. More particles leads to more mass, which leads to greater kinetic energy because you have literally more particles there. That's getting a little bit specific. So we're just looking at big picture. Did you change the temperature of the can? And the answer is no. We didn't significantly change the temperature of the can. So this would be my complete explanation. Okay, you add particles, it increases the pressure. Let's try another. If I jump to the next page, what happens if I increase the temperature of a can? Well, this is a box. So my box is closed and inflexible, just like the aerosol can. And if I'm increasing the temperature, I see the arrows are moving faster. So increase in temperature. And I know that the variable directly connected with temperature is kinetic energy. So if temperature goes up, kinetic energy is also going to increase as well. The particles are moving faster and faster. And if they're moving faster and faster, they're going to collide with the walls more frequently. They're just literally bouncing back and forth more often. And if there's more collisions, I know pressure is also going to go up. So the pressure inside the box is going to, again, be greater than the outside. We're increasing the pressure inside of this container. So pressure is going to increase. Now, the constants for this one, the volume of the box, and the number of particles trapped inside. Cool. All right, let's keep going. What if I have a piston? This is something that's in an internal combustion engine. You compress a gas and then you ignite it. Gasoline here with oxygen, and then that's what generates the power for your engine to rotate all the axles and everything. So what's the change here? Well, a piston is a metal tube that is manually compressed by the engine. This is closed, right? You don't want gases entering or escaping. That's when you've blown a piston, right? That's not a good thing. And this is inflexible. It's made of metal, and it itself manually compresses the gas. So the gas can't change its volume on its own. Now, when the piston compresses the gas, we're decreasing the volume. When we decrease the volume, the gas that's in there has less room to move around. If it's compressed into a smaller space, now the walls are closer together, which means that there's going to be more collisions between the remaining particles and the walls, which are now twice as close. And if there's more collisions, there's more pressure. So this is increasing the pressure inside of the piston compared to the outside. All right, what doesn't change? Well, the constants for this one. The number of particles didn't change. The temperature didn't change, and the kinetic energy didn't change. We didn't heat it up, cool it down, or add any more gas. Now, when you're operating an engine, typically the next step, once you compress that gas, is to ignite it, and then it explodes outward, and that force is what generates the power of an engine. But we haven't done that yet, so we're going to stop there. All right, what does the pressure inside of a tank, why does the pressure inside of a helium tank decrease when it is cool? Okay, so let's think about a helium tank, also closed and inflexible. All of these have been closed and inflexible so far. When we get to the next page, we'll talk about volume where it can change, where it is a flexible container. And it says we're putting it on ice, so I'm decreasing the temperature of the gas inside. If I imagine some little arrows moving around, I could draw some arrows in my original picture. In my after picture, I'm cooling them down. So that means my arrows are going to be getting even smaller than they originally were. So the motion of my particles, the speed that they're moving around, is going to decrease. As they move slower, it's going to take them longer to get back and forth from the walls of the container. So my collisions are going to decrease. They're just moving slower. It's going to take them longer. And if there's less collisions, I know pressure is also going to be impacted. So what happens to the pressure inside the tank compared to the outside pressure? It started equal at 1 atmosphere. Now the pressure inside is less. We've decreased the pressure. Constants for this one, moles and volume. So these are all ways that we could change the pressure of a closed, inflexible container. Now, flip over to the next page. This is where it gets a little bit more complicated, is when it's a flexible container. And when you have a flexible container, the volume of the container can change. So volume can change, which means that the volume always changes until the pressure inside the container is equal to the pressure outside. So a flexible container will always change its volume to get the pressures to be equal. So the first situation here, I've got a balloon, right? It's sealed off and I'm warming up my balloon. Now, a balloon is a closed and flexible container, which means that originally the pressure inside is equal to the pressure outside. Otherwise, it would have changed its volume. And we're heating it up. So I'm increasing the temperature, which means that the particles themselves, if I draw some arrows here, draw some small arrows in my original scenario, and then I'm going to draw some bigger arrows in my second scenario. The particles are going to be flying around faster and faster. That's the kinetic energy. They're going to be moving faster and faster. And if they're moving faster and faster, they're going to start colliding with the walls more frequently. And if there's more collisions with the walls, then the pressure inside is going to go up, which is going to cause the pressure inside to be greater than the pressure outside. Now, the balloon is flexible, so it doesn't want this situation to occur. So what does it do? The volume changes. So because it's flexible, we can now have a change. The balloon surface is going to respond. The rubber is going to respond by increasing in volume. When it increases in volume, it's spreading out. It's giving that gas more room to move, which is going to cause fewer collisions, which is going to cause less pressure until the pressure inside is equal to the pressure outside. So momentarily there's this increase in collisions and pressure inside of the container. However, then the volume responds and gets those collisions to go back to their original. So we can think about the constants for this one as really just the moles, but we also have collisions and pressure. If you were to look at it before and after, the pressure inside compared to the pressure outside started equal and it ended equal. So it changed momentarily, but before and after, we can consider it as a constant. It's a little bit more complicated when it's a flexible container. Let's try another one. A car tire. If I look at a car tire that's flat, this is a closed, flexible container. And I want to add air to the tire. I increase the number of particles inside of my flat tire. So I literally add more particles to my tire. More particles leads to more collisions, leads to greater pressure. Now, a car tire has to have a greater pressure than the outside air in order to be able to hold your car up. So in this case, we do want the pressure inside to be greater than the pressure outside. Otherwise, it wouldn't be able to hold your car up. Now, when you increase the pressure inside, this causes the volume to go up. The car tire is still flexible to a point, so it wants to expand, but it can't expand indefinitely. It can only expand until its outer limits. Once it expands too much, that's when you've popped your tire. And you'll see this sometimes in the spring when people have overinflated their tires in the winter and then it gets warm outside. So it's kind of flexible to a point. So you could argue this is inflexible once it reaches its maximum volume. The constants for this scenario are only temperature and kinetic energy. All right, last one. Why does the volume of a balloon increase when air is added? So we know that the pressure inside starts equal. The pressure inside is going to end equal. That's the definition of a flexible container. It's closed and flexible. And we are adding particles to the balloon. This is just like the car tire, except it's going a little bit more in depth. Now we do have the volume change. So more collisions, more pressure. Pressure inside is greater than the pressure outside. The volume can freely change in a balloon. So because it's flexible, the volume of the balloon is going to go up, which causes the collisions and the pressure to go down until the pressures are equal. So this is a true flexible container. Constants for this one, temperature and kinetic energy. And then if you look at it before versus after, you could also consider collisions and pressure as constants. Now we're going to keep practicing looking at these scenarios, and they can be a little bit confusing. It's just going to take practice to get more kind of comfortable with the kinetic molecular theory of gases.